to the cloud. Okay, great. So this is what we did last time. Lagrangian mechanics on R3 and on R3n. And so then I explained the idea of constrained motion. And I think that's more or less, so that was the motivation for general formulation of Lagrangian mechanics on a smooth n-dimensional manifold where this is the configuration space. And then I started to explain the elements of smooth manifolds, but it seems like now everyone knows what a smooth manifold is, and correct me if I'm wrong. Okay, so now Lagrangian mechanics on smooth manifolds. I assume that everyone knows what this is. If you don't know, then think of this as a bunch of charts with local coordinates and just think about it in coordinate terms. And then if any explanations needed, they will be in a special file. Okay, so Lagrangian mechanics is determined by the following collection of data. First, if we want to describe a mechanical system, we have to describe the configuration space. It's the space, so in mechanics, it's typically smooth manifold. It's possible not to have some kind of singularities, but let's not talk about this. So configuration space, it just means that the system is moving along in this configuration space. So for point particle, this is R3, there's 3 coordinates. For a particle constrained to a sphere, these are points on a sphere, so this is the sphere. And then the second piece of data is Lagrangian function. It's a function on the tangent bundle to Q. It's the Lagrangian of the system. And these are the data that define the dynamics. So now let's, so this is the set of data, and the main principle. So maybe I should say that it's a function of 2 variables now, where v is the velocity. It's a tangent vector to our configuration space, and q is the point, is a point in the configuration space. So this is how you can think of Lagrangian, and this is the natural way to think about Lagrangian. So the main principle is that trajectories are solutions to the Euler-Lagrange equations for the action functional. So now let me define the action functional, and then we will derive the Euler-Lagrange equations. So given the Lagrangian, given the manifold, the configuration space, we define the action functional as this. So here gamma is a parameterized path in our configuration space. So so this Q of t is just the parameterization of this path. We can also write it as function Q of t with values in Q capital when t runs from t1 to t2. And naturally, Q dot t, it's the tangent vector to this path. So I assume that these paths are smooth. So, so this is the velocity of this for this trajectory. So now, in order to get Euler-Lagrange equation, let's find critical points. Of this functional. So in order to find critical points of this functional, well, these are the points where all directional derivatives are 0. Just as I was explaining last time. So we have to, I'll just define it like this. It's DDS. So we take this path and we create, so this is one parametric family such that gamma 0 is equal to gamma. So, and we have to evaluate this at time 0. It's just the same as a directional derivative. Imagine that you have a point, and then you have a path through this point, and then the directional derivative of a function is just a derivative in the direction of the tangent vector to this path. And that's the same. It's just except that this path is in the space of path. So this is a path in the space of path. And intuitively, you can think of this as just you do the infinitesimal variation of this path gamma, and you just compute the infinitesimal change of s when you do the infinitesimal variation of the path. In terms of coordinates, so here I will write it in local coordinates. Qi on q. So this will be delta q dot I dl dvi q dot q. L is a function of the tangent vector, and q plus delta qi dl dqi q dot q. I mean, strictly speaking, this is q dot of t, this is q of t, but just I'll skip these notations to move faster. Okay, so this is the variation where delta q is just of t, delta qi t. This is simply ds of qi ts at s equals 0. This is the tangent vector in the space of path. Okay, so now we want to write this in not in terms of derivatives of delta q, but in terms of delta q itself. So we integrate by parts. The result of the integration by parts is minus d dt dl dvi q dot q plus dl dqi q dot q delta qi dt plus we integrated by parts, so we should take into account boundary terms. Delta qi dl dvi q dot q between t1 and t2. All right, so we have two terms. One is the bulk term, the other is the boundary term. So maybe I should use, so this is the bulk, That's the standard terminology. These are the boundary terms in the variation of this functional. So now we want to find critical points. So we have two terms, bulk and boundary, and they both should vanish if we really want to have a critical point. But Euler-Lagrange equations these are just equations for vanishing the bulk term. So dqi q dot q is 0. Well, before we will analyze the boundary terms, let's just focus on Euler-Lagrange equations, and let's see what kind of equations they are. So let's first do this. Let's just write it explicitly. So I will differentiate in time this expression. So then I'll have the second derivative in v, q dot q, and then q dot j, t, double dot, second derivative, sum over j. Minus, when I differentiate q, I will have the mixed derivative. Again, sum over j, dvi dqj, q dot j t, and then the last term is just as is. Okay, so this is our differential equation. It's clearly second order differential equation. So what do we want from this differential equation? We want it to have the same amount of determinism as Newton's equations do have. So in particular, we want to have the existence of local solutions, existence and uniqueness. And so let's say that we have a condition that q dot 0 is some vector. Well, we don't have to use coordinates here. So it's just, and q0 is q, and v is a tangent vector to the configuration space at the point q. So these are our initial conditions. And then by Picard's theorem, if the matrix is non-degenerate, if the determinant is non-zero, then there exists unique solution to the initial problem.
Excuse me, I heard something about metrics. I suppose that we were speaking about.
No. There is no metric.
Manifold.
No, there is no metric.
Okay.
This is just non-degeneracy condition.
Okay.
It's the usual Picard theorem. If you have the second order differential equation, really second order, then there is a unique solution, local solution to the initial value problem. Local means the local solution means for small t, for some small t. Whether the global solution exists or not, this is the main question in dynamical systems, but locally it will exist if this matrix is non-degenerate to the initial value problem. So this is this is a natural condition that it's non-degenerate. But now, of course, from physics, well, we know that the meaning of these derivatives. So this is like a mass matrix. So in R3, remember that the natural Lagrangian is mass times v squared over 2 minus the potential force. So so it's natural to require, and this is what usually is required, that this matrix is positive definite. So all eigenvalues positive, and as you say, this is equivalent to say, it's equivalent to say that this is a metric. But a priori, there is no metric. There is just this function L. Okay, so this is the usual. So the usual assumption in Lagrangian mechanics. Mechanics is that this matrix, not these partial derivatives, but the whole matrix is positive definite. There is a notion of totally positive matrices where all entries are positive. It's a very important notion, but here it's just positive definite is, that's what usually we have. Okay, so this is the third. This is an assumption on the Lagrangian, very important assumption on the Lagrangian. In particular, we will see that when we will be passing to Hamiltonian mechanics, we will use this assumption in order to make the Legendre transform in the tangent directions of the manifold. Okay, so very good, but you see, what happens if so this is one, this is an extreme case. Let's call it I. It's the most non-degenerate case. Now let's consider the most degenerate case. Not the most degenerate, but kind of the most degenerate for the second derivative case. That's the case when all derivatives are zero, identical. Well, let's look at the, so what does it mean? It means that our function is linear in velocities. It means that it's sum over I in local coordinates plus some function h of q. So, so of course, alpha I, so you remember that v is a tangent vector. In order to have the Lagrangian to be coordinate independent, so this is coordinate independent. In other words, if you go to the next coordinate chart, it will transform to kind of the same expression. These functions alpha I, they are not functions, they are only locally functions of Q. Globally, they are component of one form, differential form of first degree on our configuration space Q. So let's look at what is happening in this case. Let's look at the Euler-Lagrange equations. So then this term is non-zero, and this term is non-zero. So let's write them in terms of alpha, and so we'll have minus d dqj alpha I q, and then we have to substitute q dot I plus, and then when we differentiate the Lagrangian in Q, we will have so sum over J, we have sum over J, Q dot J, and then d alpha J, d Q I plus dh dqi equals 0. So now I just want to write it sort of in a more civilized way. So this is the same as sum over j omega ij q dot sorry, this is j. Yes. Q dot j is equal to dh dqi, where omega ij is d alpha I dqj minus d alpha j dqi in local coordinates. And globally, it defines a two-form, differential form of degree 2. And you can write this differential form as d alpha, where d is the de Rham differential. So I hope that everyone is familiar with these notions. De Rham differentials, smooth manifolds, and so on. Okay. So because omega is d alpha, as a consequence, d omega is 0. So who knows what is the name of this structure of the manifold? So now we have a smooth manifold Q and a closed differential form omega.
Symplectic structure?
It's not quite symplectic structure. This is what we want. But so far, because we don't know whether this matrix is non-degenerate, it's a pre-symplectic structure. And if we require that the determinant of omega ij is non-zero, then this pair is a symplectic manifold. And what is this equation? This differential equation is the equation for the flow lines of the Hamiltonian vector field generated by H. So we arrived to the Hamiltonian.
But this requires for our initial manifold to be of even dimension.
Yes, of course. So this is possible. I mean, this is possible only if, because it's Q-symmetric, if the dimension of Q is even. Otherwise, it's simply not possible. So if we require that it's non-degenerate, it's automatically even dimensional, and we arrive to the Hamiltonian mechanics. And we have to require this if we want the existence and uniqueness of local trajectories. So you see, if the matrix of second derivatives of the Lagrangian in velocity is positive definite, that's our case of Lagrangian mechanics. If it's identically zero, then if we still want to have the Picard theorem, the existence of locals and uniqueness of local solutions, we have to assume that this matrix that we got over here, that it is non-degenerate. Once it's non-degenerate, we arrive to Hamiltonian mechanics where on Q with this symplectic structure. Okay. So we will discuss it later. We will discuss Hamiltonian mechanics soon. But now let's just continue with the Lagrangian mechanics. All right, so so where did we stop? We have the Euler-Lagrange equations. So now with all our assumptions, this matrix is non-degenerate. So there are local solutions. They exist and unique, and we require the positivity. So this is the case that we study. But now we have to set up some boundary conditions. Why do we want to set up boundary conditions? Well, for two reasons. First, you see, Euler-Lagrange equations, they gave us vanishing of the bulk term, but we still have something from the boundary. So if we really want to have extrema of the function, of the action functional be classical trajectories, then we have to make sure that these terms are zero. But even if they're non-zero, well, we still have to fix solutions. And so far, we know only one way to fix solutions. It's the initial value problem. So let's consider something more general. So boundary conditions. So what does it mean to have boundary conditions? So let's define it like this. So I will keep using the notation. Let's call it P. It's the space of smooth parameterized path in Q. So now the definition. Gamma satisfies the boundary conditions. Oh, not the just boundary conditions. B1 at time t1 and B2 at time t2 if gamma t1 belongs to B1 and B1 is some submanifold in Q and gamma, sorry, in the tangent bundle of Q, and gamma T2 is in some submanifold in the tangent bundle to Q. Examples.
Sorry, just a question before we go on. Are there names for the cases of, I guess, the degenerate cases between Lagrangian and the Hamiltonian case?
I don't know. I'm sure people in mechanics studied them. You mean the case when
Yeah,
when you have
there's some dependence or yes,
yeah. I don't know. I mean, I was I wanted to check this in the literature for some time, but I never did. It's a very good question. So yeah, I think if the matrix is non-negative, say if the matrix of second derivatives, it has some zero directions, but on the rest of these directions, it's non-negative, then I think it's equivalent to some Hamiltonian mechanics on some kind of strange bundle. So you will have the degenerate structure. Yeah, you will have this degenerate scalar product on tangent spaces. Well,
it's
anyway,
like
it will be some kind of mix
in the two directions, right?
Yeah, exactly.
Yeah.
So yeah, so you will have presymplectic structure in the in these zero directions and the Lagrangian structure in the non-zero directions, and then you can do the Legendre transform, which we will discuss soon, and then you will get the, I suppose, some kind of strange symplectic manifold and Hamiltonian mechanics on it. But I never saw any serious discussion of this. All right, so some examples. There are plenty of examples, and we will discuss them later in the Hamiltonian setting. But now just examples. First, the one that we already discussed, B1 is just a point, V0, Q0 in TQ, and B2 is just the whole TQ. So, so we are looking for trajectories with given velocity at the time zero. So this is V0, this is some V0 prime, and so on. So we fix the velocity and we fix the trajectory, at least locally. Second, kind of ballistic problem. So we fix B1 as TQ, and B2 is Q1, and B2 is TQ2. So we didn't fix the velocity at the initial point, we didn't fix the velocity at the target point. All we want is, we want to move in time from T1 to T2, from the point Q1 to the point Q2. It doesn't matter what's the initial velocity, what's the target velocity. It's determined by our desire to move from this point to this one in fixed amount of time. So these are two examples, and one can discuss more of them. The question is, for which of these boundary conditions we really have these boundary terms vanishing. So for this, let's make a definition. And this definition, I'm not sure. I cannot really. I can't find good words to explain why it's important in classical mechanics. But as we will see in quantum mechanics, it will be important in the semi-classical limit of the quantum mechanics. Definition: boundary conditions V1, V2 are variational if delta S gamma is 0 on solutions to Euler-Lagrange equations with these boundary conditions. So, in other words, if in local coordinates oh, sorry. This is the velocity at the point. This is the point equals 0 for a equals 1 or 2. Assuming so, just yeah, what does it mean with these boundary conditions? It means that delta Q TA is a tangent vector to the boundary manifolds B A. So remember that a boundary condition is a submanifold in the tangent bundle. And Q dot TA QTA is in this BA in the tangent bundle. So this is a little bit clumsy definition. I didn't want to write it in coordinate-free way, but it's possible. So you can do this at home. Write this geometrically. In a coordinate-free way. So let's analyze these two examples. First, when V1 is a point V0, Q0, and then V2 is just the whole thing. Because we fix, so this is QT1, because we fixed it, delta QI T1 is 0. And so at T1, we are okay. This term, this expression is, and when I write, sorry, I forgot to write here sum over I. Sometimes I will use these Einstein notations of summing up over repeated upper and lower indices. So if you don't see the summation sign, that means that I omitted.
Excuse me, I have a small question concerning the dimensions of these boundary conditions. Is it true that the sum of dimensions of these boundary conditions are equal to the dimension of our initial manifold or not?
That's a very good remark. So we will come to this. So far in both of our examples, this is true. And just, you know, I will write it on the board, but I can say it in words. If you impose less conditions, you will have infinitely many solutions to this boundary problem. If you impose more solutions, if you impose more conditions, then you may not have solutions at all. So when the sum of the dimensions is equal to the dimension of the tangent bundle, that's the critical number when you have just enough conditions to fix the either unique trajectory or finitely many trajectories. Okay, so in this case, we are okay at T1, but then at T2, we are not okay at all because we have no conditions on delta Qi T2, and so which means that this expression should be 0, and then if Q of t is determined by the initial data, that means that this will be conditions on V0, Q0, which is a contradiction because we fix them arbitrarily. So that means that this is an example of not variational boundary condition. So this is not variational. Okay. And the other condition is B1 is T Q1Q, B2 is T Q2Q. Well, that's a great boundary condition. This is Q T1, this is Q T2, which means that the variation at T1 of Q is 0, the variation of Q at T2 is 0, which means that these are variational boundary conditions. So these boundary terms, they vanish on the nodes. Okay, so so the dimensions when the sum of the dimensions is equal to 2n, we have a good chance, and it's what happens typically, unless something very weird is happening, to have either unique solution or a discrete set of solutions. Again, typically finite. Okay, so what else do I have to say? Yeah. Well, I think this is what I wanted to say about boundary conditions. I forgot, when do we have to make a break? If you prefer, we can go without a break. But you are the master of Tsinghua. So
is this a university course? I thought it was of your own volition. So
it's my own condition, yes, that's right. But I was trying to follow the timing of the university.
Okay. I'm not sure actually. It's usually something like 45 minutes or 15 minutes and then a break. But so yeah, I suppose sometime around now.
Okay. And
yeah.
do you prefer to go just so we can just go until 8:50 without a break? And you can interrupt me anytime.
Yeah, I mean, your audience seems very young, so you know, they've got plenty of energy, and nighttime is like the best time for them, right? So
Okay. Any
that's my
objections
guess.
against moving without a break?
No, no objections.
Okay, great. So let's just move
By
on.
the way, I did have a question
Uh-huh.
about the first case when you didn't have a variational boundary condition. So is there a reason why DL dv2 can't be 0, or are we just saying that it's not 0 in general?
It can be 0.
Right. So for special L where it is 0, is it still called variational in that case, or?
I think this is a singular case when it's 0 at the boundary.
Mm-hmm.
So I think, so let me think about this question. I never thought about this. And later on, you will see why I never thought about this. Because the Lagrangian mechanics is not really a good way to sort of to talk about such boundary conditions. We will see that in Hamiltonian mechanics, these variational boundary conditions, they have very simple interpretations. This should be Lagrangian submanifolds.
Mm-hmm. Okay.
So I just, I want to return to this discussion. Thank you that you stopped me. So we have two different cases, very different cases. You see, in one case, we fixed both the velocity and the coordinate at the initial point, and we didn't fix anything at the target point. In the other case, we fixed coordinates in both initial and target point. And quantum mechanics, there is this indeterminacy principle that you cannot measure both coordinates and momenta at the same time. So in some sense, you can see the kind of traces of this uncertainty principle in classical mechanics, and it's in here. So it says that if you want to have variational boundary conditions, then you cannot fix velocity and coordinates. You cannot fix more than half variables in one place. So, so that's the.
By the way, is there any intermediate examples when so in the first example the dimension of the second boundary is the maximal, and in the
yes, of course. Let's consider the special case when Q is just Rn. So then the tangent bundle is trivial. It's Rn cross Rn. These are the velocities. These are the Qs. And in this case, you can say that V1 is the case when you fix, let's say, velocities for the first k coordinates you fixed. So this I fixed. You fixed all coordinates. And if you want to have solutions to equations of motions, you should fix at B2 coordinates qk plus 1, qn, for example. So then you have, so the dimension of these two plus the dimension of B1 is 2n. So you have local trajectories. Well, what does it mean local? If you can travel from B1 to B2 in sort of in small amount of time, then I suppose the version of Picard theorem says that there will be finitely many, typically there will be finitely many of those trajectories. So in this case, so this is not variational. And that's an intermediate one. So you can, so basically to have a variational boundary conditions, you have to fix n variables at T1 and n variables at T2. And we will see very soon when we will discuss Hamiltonian mechanics why this is the case. Okay. Any other questions about boundary conditions? Okay, let's look at one example. So let's suppose that our manifold Q is n-dimensional. It's embedded into some kind of n-capital dimensional manifold, n less than n. So let's assume that Qi are local coordinates here. X alpha are local coordinates here. So let's take the massive particle in Rn with the mass m. So this is x alpha dot squared over 2. And remember, just as we discussed before, let's, by choosing a sequence of potentials that is approaching to kind of delta function supported on Q, so that's the delta distribution. Supported on Q. We can restrict, we can constrain the motion to Q. And because for every sequence of these potentials, our trajectory is still a critical, so a critical point of the action functional. So for the limiting trajectory, for the trajectory on Q, our trajectory is still solution to the Euler-Lagrange equations. So let's just write what Euler-Lagrange equations mean here. So, so Q is embedded. Let's assume that we have a function f that's describing this embedding. So in local coordinates.
Sorry, are we looking for the critical critical points of our Lagrangian L in Rn that lies in Qn? Or not? So we have additional condition.
Yes, exactly. So that's what I meant. So now we're looking for critical points as gamma, which is the integral from T1 to T2, L0 Q T dt, well, Q dot T dt, and this is just m over 2 sum over alpha x dot alpha over 2 squared, where x alpha t is f alpha of qt. And gamma is a path in Q, which is embedded in Rm. So our Lagrangian is just, it's the restriction of this Lagrangian to parameterized paths that lie only in Q. Okay. Did I answer this question?
Yeah, thank you.
Okay, so then I'll use the chain rule. So this will be Q dot I, again, sum over I, T dx alpha, the Jacobian of this, well, suppose I can call it Jacobian. So, and that means the Lagrange, the action functional, I can write now as the integral from T1 to T2, M over 2, sum over alpha ij, and here it will be, well, okay, I better write it like this, sum over ij from 1 to n. And again, I'm emphasizing that these are local coordinates. It's very convenient to use local coordinates, but if you don't like local coordinates, you can always write it in coordinate-free way, but it will be messy in my point of view. So dx alpha dqj. Of course, this all depends on qt. So this is this special expression, and then q dot I, q dot j. And of course, what is this? This is gij qt. This is the induced, this is the metric on q induced by the Euclidean metric on Rn and the embedding f of q into Rn. And so in terms of intrinsic geometry, I can write S gamma as the integral from T1 to T2, M over 2, and here sum over ij, gij qt, q dot I, q dot j, dt. And now I can write it just like this, T1 to T2, M over 2, and then here this is the metric on Qn as a scalar product on tangent spaces. This is the coordinate-free way.
May I ask a question?
Yeah.
Do we have some assumption about embedding F?
About what?
About F.
Oh, you
That
mean
is
this?
smooth or it's
Yeah,
compact?
Everything, yes, it's smooth embedding. Yes.
Okay, thank you.
Mhm. So this is the free geodesic motion on Qn. Geodesic meaning that critical solutions to Euler-Lagrange equations are geodesic curves on the metric Q with the metric induced by, with the metric Q induced by the embedding.
So the natural question arises: is it true that for each Riemannian manifold, or for each smooth manifold with metric, there exists such a Lagrangian and such embedding f that the geodesic motion on this Riemannian manifold is describes some physical system with Lagrangian and smooth embedding f.
I didn't understand the definition of a physical system.
I mean, we've been describing the we've been describing some motion, some motion provided by the Lagrangian L.
Yes.
So the question is, and then this Lagrangian induces a metric on on our manifold Q.
Yes.
And the question is, is it true that all positively defined metrics could be obtained in such a way?
I mean, your question is purely geometric. Is it true that any Riemannian manifold can be embedded into a flat Riemannian space?
Not really.
And a shame, but I don't know the answer to this question. Yeah, is it true?
I have no idea. I'd be
it's
surprised if it was,
true.
but
Is it true?
I think it's true when the dimension is like more than double. Like if n dimension embedding into something 2n plus 1 or greater, like
Okay.
you can
Nash
embed it.
embedding.
Yeah, Whitney embedding or something like that. Yeah, like n versus something greater than 2n plus.
I suppose there could be some problems with curvature. Like if you embed something with intrinsic curvature, you can't embed it in flat space. But probably I might be wrong. Okay, I will Google this geometrical question after the lecture.
But I think you have the answer to this. So, Bonjao,
Yeah,
can
I
you
think
repeat again the answer to this?
I'm not sure what it's called. Whitney embedding. It's like any manifold could be Nash embedding. Any manifold could be embedded. Like n-dimensional manifold could be embedded in Euclidean space of dimension greater than 2n plus 1 or greater than equal to 2n plus 1.
Okay.
Oh, okay.
Okay, thank you.
Thank you. And just similar to this, say, suppose that you have one Riemannian manifold embedded in the other. And such that it's a metric embedding. Then, of course, if you have a geometric flow on M2, which belongs to M1 with the induced metric, then it's also geodesic flow on M1. So it's the same as here, the same as before. So if you have an embedded Riemannian manifold, if you want to find the geodesics, all you have to do is you have to look at straight lines in the ambient Euclidean space, and then no, sorry. I was thinking about projections, and they do exist in integrable systems, but not here. Okay, so let's stop here. Let's stop here to talk about Lagrangian case. And now, if there are no questions, we still have a little bit of time and a little bit of energy. So let's say 15 minutes. So I want to say a few words about the Hamiltonian mechanics. So any last questions about the Lagrangian mechanics? So you see, now we, in some sense, we kind of making, mathematically, we're refining the problem. Because so far in the discussion of Euler-Lagrange equations, we didn't have good tools to describe conserved quantities. What does mean conserved quantities? It means, let's say, functions of functions on a tangent space which are constant on solutions to the Euler-Lagrange equations. And one can argue that Hamiltonian mechanics is, I mean, one of its strengths is that it gives you almost immediately a criterion, sort of what kind of functions they should be. Okay, so what is the Hamiltonian mechanics? So first, let's look at the very important mathematical tool which gives us a passage from the Lagrangian to Hamiltonian mechanics. That's the Legendre transform.
Wait, sorry. I did have a question for something. I'm just going back
Yes.
slightly.
Uh-huh.
So the point about using potentials to like asymptotically, well, I mean to make things well, to constrain the motion to Q. That's the part that I sort of, I can believe it, but I'm not really sure what that means. What sort of, I mean, is it because the potentials are causing the Hamiltonian to be slightly more negative on Q or something like that? I'm not sure.
You just said the right word, Hamiltonian.
Okay.
So if you don't mind, I will answer this question after we will pass to the Hamiltonian framework.
I see.
It just will be more clear.
Okay.
The kind of I can answer to this question now. So you see, you have conserved quantities, the energy for any Hamiltonian system, and this constrained potential simply means the following: that you say you fix certain you fix the value of your Hamiltonian, and you're looking for trajectories with this energy value. And then, no, yeah, I think it's very difficult to answer. For me, it's very difficult to answer this question now. It will be,
okay, yeah, sure.
It will be much easier to answer it once we have Hamiltonian tools.
Yeah. Okay, thanks.
So the Legendre transform. So let V be a real vector space, and F is a function on this vector space. So definition: Legendre transform of F, when it exists, is the function on the dual vector space, defined in this way. It's the maximum, minimum, let's say maximum, over X. Well, it's a vector space, so it's V. and then L of V, the value of the linear function on this vector V, minus f of V. So theorem f is globally defined if well, I don't want to give the necessary and sufficient conditions, but necessary sufficient. So necessary condition is that if f is convex function in V. So an example, well, so here is an example of a convex function that is not necessarily smooth. Say here we have an angle, and then it goes like this, and then it goes like this. So that's a convex F. It may have these flat parts. So strictly convex well, I'll put it as a definition. F is strictly convex if there are no flat parts. So convexity means that, well, for a function, it means that if you take a tangent line, then the function will be on one side of the tangent line for any tangent line. Well, in this case, for any straight line, yeah. So like here you have two tangent lines. The function is on one side of this tangent line. So if there are no, and then if f is strictly convex and differentiable, that means the matrix of second derivatives is positive definite. So that's something like this. Okay, so assume f is strictly convex by differential, I mean sufficiently many times differentiable and smooth. So then it's quite clear that the Legendre transform can be written as this: V, let me call it star, minus f of V star, where V star is the unique critical point of f. Oh, sorry, not of f, but of LV minus FV in V. Okay, so this is the definition. I mean, this is the definition. This is the theorem. But now, well, V is a finite dimensional vector space. So V double dual is equal to V. And so the question is, what if we will do Fourier transform twice? So double Fourier transform. Now it's a function of V.
Sorry,
Is equal-
Fourier or Legendre?
Oh, the Legendre transform.
Okay, thanks.
Sorry. So it's equal to F. If F is convex. If F is not convex, then double Legendre transform. So if not, if F double dual is defined, but F is not convex, for example, if you have something like this, then F double dual is the convex half of F. In other words, it's just like this. Then you connect this by a straight line, and then it goes like this. You connect it by a straight line. So these notions are very important in various questions of optimization, in thermodynamics, in many applications. So for us, we consider only the case when it's strictly convex and smooth. We're passing from Lagrangian to Hamiltonian. We need only smooth plus strictly convex. Okay. So this was just the digression to Legendre transform. You know, if you really want to have fun with the Legendre transform, I really advise you to solve something like this. Let's say that you have a function. Here it's a straight line. F of x is equal to alpha x. Here it's the, I don't know, ax squared for the appropriate value of a, so that the function will be continuous function here. So a squared equals to alpha a. And then this is something like f of x is bx squared minus, I don't know, cx, so that it's f of 0 is 0. Let's say x squared. So just for fun, find the, if you've never done these problems, this will be really nice. Find the Legendre transform, which is simply the following. It's the maximum over x, yx minus f of x, where f of x is defined here. Okay, so this is the Legendre transform. I think let's stop now. So next time is passing from Lagrangian to Hamiltonian function. Lagrangian will be a function on the tangent bundle, and the Hamiltonian is a function on the cotangent bundle. And so the definition of the Hamiltonian is just the Legendre transform in the tangent directions PV minus LVQ, where P is in the cotangent space to Q. So we will take this definition and we will work with this definition next time. We'll derive the Hamiltonian dynamics with all its consequences. And then I will maybe one more lecture on Hamiltonian mechanics. We will discuss the Hamiltonian mechanics on an arbitrary symplectic manifold and the variational principle, the analog of the action, the Hamilton-Jacobi action for the Hamiltonian mechanics. And then after this, we'll pass to quantum mechanics. Okay. Well, thank you for the heroic effort to stay that late for all who is in local time and to come from far away who is not in local time. Okay.
Thank you for the lecture.
Yep. See you next. Oh wait, so please don't forget to send me an email. Just this is the email. Please send me the email with so that I would have your email, and then I will send the doodle, and we will fix the new time, new day. So same time but new day. Okay.
Okay, see you.
Bye bye.
Okay,
Thank
thank
you.
you.
Thank you. Goodbye.